All right. Can you say something, Kennedy?
One, two.
Hey, all right. Can you guys hear us? Yes. All right. Sounds good. Hey, everyone. What's the new Discord server? The new Discord server, I think it's for. Taurus does not have a camera. Do you want to turn on your camera? I can show your camera.
Yeah, I guess you can.
Sure. I'll just show your camera. Sure. This is Kennedy. Um,
Hello? No, I
and
don't have
yeah.
Discord. I just connect to it virtually. I mean,
Oh, can you not decrease the quality? Oh, that's a bit of a shame. I actually can't do much about that. If Twitch doesn't give me re-encoding, then I actually can't do that. This is just a little server I use for video calls. This is not a public server. It's cool. So yeah, I guess we can take this time and talk about the contest. What did you overall? What did you think about the contest, Kennedy? How did it compare to your expectations?
well, it went fine. I mean, I guess overall, like problem difficulties were pretty good. Like, I mean, no huge steps, and in general, it's pretty balanced. I mean, it's kind of a normal contest. It is not like it doesn't have like any mind-blowing ideas, I think, but it's kind of like you work through. You can work through the problems, and I think that's pretty good. I mean, I enjoyed
Mhm.
the experience.
Yeah,
What
yeah,
about you?
I
What do you
enjoy it.
think?
I enjoy problems where you just work through it. Mind blowing ideas are too hard for me. But yeah, what do you think about the end up like the solve counts at the end? Were they pretty much what you expected?
Well, I guess I expected more solves to G, but
Mhm.
I'm not sure. Like, it's a bit. It depends on how you approach it because I think that many people might just not come up with easy implementation ideas, and
Mhm.
problem G could just look like very tough to them.
Mhm.
Or maybe another way, like I'm not sure. Maybe another reason is that when you after you solve F, it's quite clear you go for G or H, right?
Mhm.
And also like H had an early accepted submission, right?
Yeah, yeah. I checked
After
during the
1 hour.
contest and that was Rainboy, which makes sense because
Yeah, yeah, yeah.
he does the thing where he starts from the end.
Yeah, so I just mean that maybe like it's kind of a choice of whether go for G
Yeah,
or go for H, and
yeah.
I might assume that many people went for H because it
Mhm.
looked more attractive.
Yeah, yeah.
Maybe that's why it's also G fell a bit, and also H was like it costs more, right? So
Yeah, yeah. Yeah, yeah. H was worth a lot more. So in the end, I think going for H was like a ended up being better if you could do both. Or, but yeah. Cool. Do you want to let's take some time and go through the problems while sys tests are still running. I don't know how
sure.
far they are right now. 20 some percent. Okay. Cool. Yeah. Let's just go through the problems. I saw someone say that problem A's idea was fab. Do you want to talk about problem A really quickly?
Yeah, sure. So problem A was created because actually I thought that problem B could be problem A, but
Mhm.
Kan can I don't know how to pronounce that. He said
Yeah.
that probably B is too hard for A, so I just came up with this one.
Uh-huh.
Yeah, basically, I mean yeah, I mean the problem itself asks for something not trivial, right? So you want to represent n as the sum of some numbers, but numbers only consist of zeros and ones, right?
Right.
So the first thing you can notice is that like you can find like if you add only a small amount of numbers, you cannot have large values in digits, right?
Mhm.
So if like consider the largest digit in the number, and if you use less numbers than the largest digit, you just cannot reach that value in the digit. So you have to use at least as many numbers as the value of the largest digit is, right?
Yeah.
And
Yeah.
then
Yeah.
it's kind of easy to see that this is reachable. You can always, like, for each digit, you just choose like any numbers and put ones into that positions, right?
Yeah. Yeah.
I
Yeah.
don't know.
It took me
I mean,
it
I
took
mean,
me a minute to
like, yeah,
realize that. Sorry, what were you saying?
Mhm. Yeah, I mean, the first solution came after like 37 seconds, so
Yeah, yeah. I was just gonna say it took me a minute to realize that you can that you don't need the. It took me a minute to realize that you can't do any better than the largest digit. Like it was pretty clear to me from the start that if the largest digit is like a 5, you can do it in 5 things because you just like you take all the 5s and then you take all the 4s and 5s and you take all the 4s, 5s and 3s and stuff. But I didn't really realize that. It took me a minute to realize you can't actually do any fewer than that. So
yeah.
that was yeah. Yeah.
No, I guess it was a fine problem A. Like, I think it was quite easy for problem A, but
Yeah.
that's
Yeah.
kind of
Yeah.
a good thing too, so that more people can come to the contest, and also it baits people into, like, after they quickly solve problem A, they have to do the contest, right? They can't just leave.
Right. I think one other funny thing about A is you can solve it without reading the number in as an integer. You can just read it as a string and print out the max character.
Yeah. That's
So
actually what I did.
I
Like, I have a
I don't know if anyone
two-line
did
Python
that.
code.
Yeah, the Python code should be like super short. You just like map max or something.
Yeah.
Yeah. But cool. That's yeah. So that was problem A. Let's talk about problem B. Problem B. You said this was originally going to be problem A, right?
Yeah, I thought it could be problem A, but maybe it requires too much. I don't know. Like, you have to be careful, and maybe if you're not experienced enough, you have to output a matrix. So that's probably
Right.
indeed a
Right. Right.
bit tough, right?
Right. Yeah, so the problem was that, for those of you guys who haven't read it yet, the problem was that you're given a width and a height, and there's a rectangular table, and you want to place plates on the outer boundary of the table. So that's like the first row, the first column, the last row, and the last column. And you have to place them so that no two plates share either a common side or a common corner. And we're trying to place as many plates as possible in any such way. And so the way I solved it is by realizing that if you consider like a corner cell and the 2 cells next to it, all 3 of these are touching at a corner, so you can have at most 1 plate in that corner. And if you have at most 1 plate in that corner, then you might as well put it in the corner cell, right? Because that touches like the fewest other plates. So if you just place it in the corner cell, I just placed the 4 corner cells and then placed all the edges, and then like alternated down all of the edges while avoiding those corner cells, avoiding being too close to those corner cells. Was that the kind of solution that most people use? Do you think, Kennedy?
I don't know about most people. That's definitely what I would do. Like, the thing is, you come up with a solution, and like, you also want to prove it, right? Even though,
Right.
and actually, like, in this problem, you kind of have only 4 different cases, right? Only the parities of even 3, right? The parities of the
Right.
dimensions matter the most.
Mm-hmm.
And then probably
Right.
if you can solve test cases like 5 times 5, 5 times 6, and 6 times 6, you probably are good to go, right?
Mm-hmm. Right.
But other than that, yeah, I think that it's nice to realize that corners can always be taken. And after you fix the corners, you just solve each side independently. But
Mm-hmm.
also, like, this problem kind of accepted every solution you could come up with. It's kind
Mm-hmm.
of hard to make a suboptimal solution. Because, for
Mm-hmm.
example, if you just go through all the cells in row major order and just try to put a plate into a cell if there's no neighbor already,
Mm-hmm.
it passes too. Yeah, like,
Mm-hmm.
I
Right.
mean,
Right.
yeah. So basically, whatever you do, if you use all the space, you probably are good.
Right. Yeah, it's actually not even. Yeah, it's actually pretty hard to actually screw up. To like get yourself in a trap if you just do some greedy thing. So that's pretty interesting.
Yep.
Yeah, one thing about problems like this is that like even though there are a lot of solutions that work, it's also very easy to get in the trap of just writing a lot of casework, right? And so this is the type of problem I feel like where if you think about it a little bit and you like try and simplify your cases on paper before actually coding, it can make your life a lot easier. It's pretty easy to accidentally like, you know, come up with 8 cases that you need to handle all separately. Something like
I
that.
agree. That's actually something that can be applied to a number of problems in this contest, I think. But yeah, we'll talk about it later.
Yeah, yeah. All right, cool. Let's move on to C. Problem C is about open cup. I see. Uh,
Yeah, it is.
so problem C is about this scoring system where there are a bunch of contests, and in each contest you can get some number of points between 0 and 100. And the contest is nice to you, so if there are K stages, then they take the lowest K over 4 scores and they drop them. So only your K minus K over 4 highest stages are taken. Highest scores are taken. And so as of, maybe you've done like 9 contests so far, and we want to know like if there are more stages, you have more opportunities to catch up. So how many more stages do you need to do to catch up to a given team? And so yeah, you know how many stages are completed, and you know their scores, and you're trying to figure out how many more you need to catch up. Yeah, there are a couple ways of solving this. Some people in chat are saying binary search. You actually don't even need binary search. You can just linear search. But I think the first observation, right, is that for each future stage, you should assume that you get 100 and Ilya gets 0, right?
That's for sure.
Yeah.
I mean, that was
so
not
that you can catch up.
actually like,
Yeah.
it was not described in the statement directly, right? It was only asking like in the best case, but it's kind of obvious, right?
Right. The best case should be you doing as well as possible and Ilya doing as poorly as possible. And then you can just you can actually some people say you can binary search on answer. Some people are saying you can binary search on answer, but you can also just linear search on answer. If you compute the prefix sums of the AI and the prefix sums of the BI in sorted order, then you can very quickly identify like what would be my score if there are K extra stages. Because if you keep this many, if I were to keep like 10 scores and maybe there were like 4 extras, then I should just take 4 times 100 plus my best 6 scores, and Ilya's would just be their 10 best scores. So if you sort and then linear search, that actually works. Some people are saying binary search, that also works. It's a little bit tricky to prove that binary search is actually monotonic, right? Is that obvious? That should be pretty obvious.
I mean, I guess. Yeah, it would take a little bit to actually prove it, but it's kind of natural, very natural, right?
Yeah.
And also, there are a lot of approaches, like you described most of them. Like what I would add is actually you can also abuse that the numbers are at most 100. So you can just you can just count how many stages you have with each score. And then after you do linear search, you can find your overall score in like traversal of the array of size 100 instead of n.
Right. So you can actually do linear search with 100 with O of 100.
Yeah.
How many extra stages do you actually need?
Any ideas?
So so if you have n extra stages, then you're definitely winning, right? Because you have n 100s and Ilya has n zeros, and so your 100s like beat all of Ilya's original 100, and your zero, like Ilya's zeros, all lose to your zeros. Is that pretty close to tight?
Well, I mean, if the first n of your scores are zeros and their scores are 100s, right? You need n exactly n to catch up.
Right.
Yeah. So n is the exact upper bound.
Yeah. If you need to be strictly better, is it something like 4n? Actually, it might just be n plus 1.
Yeah, n plus 1, I think is correct.
Okay, yeah. Interesting. Okay. What's the difficulty of this problem? I have no idea what do you think is the difficulty of this problem? I'm not very good at the rating difficulty thing.
Yeah, I don't know sure, but anyway, I think that like
Yeah.
this problem is kind of straightforward
Mhm.
for the top guys, but overall it
Yeah.
allows a lot of different approaches. So like
Yeah.
even in the chat you can look like you can
Yeah.
see like binary search, linear search, priority queues, vector, deck, I mean
Yeah.
whatever. So
Yeah.
you
Yeah.
can just pick your
Yeah.
data structure of choice.
Yeah. Rakesh asks how tough pretests are. Were pretests all pretty strong for this whole contest?
Yeah, I think that mostly like only a small fraction of solutions failed in all the problems. Yeah.
Mm-hmm. I see. I see.
I don't know. Actually, like it's kind of a philosophical question if that should be the case, because
Mm-hmm.
I see a lot of people like complaining that, like saying that if protests are weak, then I don't know, like the contest is bad. But that just honestly to me just makes zero sense.
Mm-hmm.
Because like there are a lot of contests where you just don't even get protests. Like protests don't owe you anything,
Right.
and like that's normal. I mean that's fine.
Right.
It's still a contest. Like you have some protests, so you're given some guarantee that your solution was tested, but you're not guaranteed that all the corner cases are there. So you still have to
Right.
test yourself. It's not
Right. Right.
only testing systems job, right?
Yeah. Yeah.
But I don't know. Yeah.
Yeah. I
Anyway,
think the one thing I
I
do,
mostly
the one thing
strong
I do
points.
think pretests should do, I agree that I think people like assume pretests like people are too reliant on pretests, and like there are a lot of contests that don't give feedback, and I think it's Codeforces is like a little more interesting if it's somewhere in between. But I think one thing is that's important generally for pretests is to include like at least one max case so that you like at least roughly know the timing of your solution on the judge. I think that's like something that is pretty nice and people try to do at least.
It's kind of nice because it just saves you time, right? But you can
Yeah.
also test yourself if you really
Yeah,
want.
you can also
I mean,
custom test yourself. So I guess it's not a
yeah,
huge deal.
I think, yeah, personally, I think that the worst thing about pretests is that you actually don't know them. Like
Mm-hmm.
you don't know how strong they are. So
Right.
if there is some corner case you like considered, you submit, you get pretests passed, but you don't know
Right.
like is there such a case in pretests, and should you
Yeah.
go to try to hack some people?
Yeah.
Or maybe it's included and then you just cannot. So
Right. Right.
that's probably the worst thing. Like it's not
Yeah.
transparent. So maybe it makes sense to just make protests as strong as possible.
Yeah.
And
Maybe.
anyway, like protests are a means of not like having too long testing queues, right?
Right. Right. Yeah. Yeah. Cool. So let's go and talk about D. D is a pretty interesting problem. The way it works is that we're trying to build a derangement. I guess you can call it a derangement or you can call it a permutation with no fixed points. So what we're trying to do is there are n people, and we want to assign each person to a different employee BI, and so that the BI form a permutation, and also BI is not equal to I. So you have to form a permutation so that no one is matched to themselves, maps to themselves. And also you're given this array AI, which is like kind of the target, and you want to make as many of the BI equal to AI as possible. And so, yeah, that's kind of our goal. So some people are saying you can solve it with bipartite matching. I'm kind of surprised. I didn't think bipartite matching would run in time. But
Well, I did not try to. I guess I don't know. Yeah, I mean it should be like still like n square root of n, right?
yeah, it should be like fast. So bipartite matching is
Yeah.
quite fast, especially in
Yeah, so
drafts like
like
this.
one way of formulating the problem was like it's not if you were not just given one wish for every employee, but you could be given any number,
Mhm,
then yeah, for sure you would need some kind of matching.
mhm. Right, right. But as it is,
But here
because
you
there's
don't.
only one wish, you can kind of do this greedy thing, where you just match up the employees according to their wishes as much as you can, and then if you have leftover employees, they must have like their wish must have been taken by someone else's wish. So they're kind of like already guaranteed. You're kind of already guaranteed to lose one fulfilled wish, and so then you can just match them up. However, and it turns out the only case where you can't just match them up into an arbitrary arrangement is when there's one unmatched person, and then I did like a little bit of a special case if there's one unmatched person to try and fulfill their wish, and if possible. So
Yeah, sure. So
yeah,
if you think about this problem in terms of graphs, right?
yeah,
You have a graph
hmm
and you want like you're given a functional graph actually, like the graph
hmm
where every vertex has exactly one out degree.
uh-huh,
It's called functional. And so yeah, you have to pick some edges and like you have to find another graph which contains only cycles of
right,
length at least 2, so that it shares as many edges as possible with the
hmm
initial graph, right? So
right,
yeah, for each vertex, you first can choose any incoming edge and remove all the other edges. So you
right,
make, because you cannot fulfill more than one. And then after you do that, every vertex has at most one in degree and at most one out degree. So
hmm
our graph becomes a collection of cycles and paths, right?
right,
And also, we could have isolated vertices, but we can say that those are paths of length 0.
uh-huh,
And we don't need to do anything with cycles. And then we can just take the paths and connect them into one large cycle.
right, right,
And again, yeah, this would not work if we only have one path of length 0, with one vertex. Then we
hmm
cannot create a cycle of length 1. Yeah,
right,
so yeah, you could just fix it on the spot, right? If
hmm yeah,
like, yeah, you just pick the edge that was actually going to be out
right,
going from this vertex and
yeah,
remove the other edge, and you can like insert this
splice them
vertex
in,
into the cycle, right? Yeah.
yeah, yeah, yeah. Were there
Another
other
way to
approaches that
fix
you were
this,
thinking? Yeah.
yeah, sure.
Were,
Sorry.
sorry, were there other approaches for fixing this kind of case?
Yeah. Okay. So the other approach could be like initially you try to like you pick just arbitrary edges incoming into each vertex, right?
hmm
But you could prioritize edges from vertices with in degree 0.
hmm
Because like the only case where when you fail, it happened because you did not pick an edge coming from vertex with in degree 0, but you picked an edge coming from vertex with in degree at least 1. So
hmm
if you just, for vertices which don't have incoming edges, you should just pick edges out going from them if you can. Like you should start with those edges. And if you
hmm
do that, then you will not have the corner case. Um,
hmm
yeah, like this is the only case, and it won't
Right,
happen just.
right, right. Interesting. Um, yeah.
And yeah, so and also there is a different approach, which could be just randomization.
hmm
Do you see what I mean?
Um, do you just pick a random in edge for every vertex and then
Yeah, you start
hope it
with that,
works?
and then yeah, but
Uh,
also you
and
have
then
to
what? You just
just
put
do
you just
something,
take
right?
everyone else and shuffle them until it doesn't have any fixed points, or
Yeah, for
less crazy
example,
than
like you can just pick a random incoming edge in each vertex, and then you just pick all vertices without ingoing edges, with all vertices without outgoing edges, and you just try to shuffle them and match.
uh-huh.
And yeah, like the number of derangements is approximately n factorial over e, right?
Uh-huh. Right. Right.
So the probability that a random permutation is a derangement is quite high.
Right.
So yeah, you should be able to finish in constant expected time.
Interesting. Interesting. Yeah. So I guess a lot of this random swapping and random shuffling actually would just work for this. Um,
Yeah.
it's pretty interesting. Um, uh, really quickly, Crazy Money. If you want to rewind the stream, you can go to Twitch. You can actually. I think this is the right link. Uh, yeah, you can go to videos, and if you click on this stream in the videos, you can rewind it there. Can we solve it by hop, crop, carp? So to solve this problem with matching, we talked about this a little bit earlier, but one way to think about it is, let's see, how do you solve this by matching? What I would do is I would set up as a min cost matching, where wish edges have cost 0 and non-wish edges have cost 1, and we also delete, and like I to I plus 1 has cost infinity, or I to I has cost infinity, or just like it does not exist.
But like you have n square edges, right?
Yeah, that gives n squared edges, but you can just do it implicitly because most of the edges don't matter.
I guess, yeah.
Because most of the edges won't get touched. I don't know if that's what. I don't know if that works or runs in time.
A little bit overkill, just a little bit.
Yeah, yeah. But yeah, that's the greedy. Yeah, but it's something like that maybe works. The greedy algorithm is pretty much you just try and match someone as long as their wish is not is unmatched so far. Can I show my greedy implementation? Okay, I'll pull it up really quickly. Yeah, we can move on to E pretty soon. Pretty much you just like if it's not used, you match it, and then you go through and you find all the unused people and you like just pair them up in a cycle, and then if there's exactly one unmatched person and they accidentally got matched themselves, then we do a little bit of a special case. But the main greedy is just like if AI equals I. I guess it turns out that AI never equals I. I didn't realize that, but it doesn't really impact the solution. If their target is unused, then we just use the target and say BI equals AI. So you don't need too much data structures. I can add channels based on roles on my main server. Why did I create a personal server? I don't know. It's easier than managing too many roles. I mean, yeah, it's not a... There's no like real reason. I also created the server before I created the public server. Anyways. Okay, cool. Let's go on and talk about problem E. Some people were asking about E earlier already. And so for problem E, we're given a string, and we're trying to minimize the maximum value in the KMP array. And so what this maximum value of the maximum value here is the maximum length of a substring that matches a prefix of S. Sorry, we're given a string and we're asked to reorder the letters to minimize the maximum value. And so the statement's a little complicated to explain verbally, I guess. But is it required to know KMP? It's not really required to know KMP, but if you understand KMP, like I would say that it's required to like know strings a little bit and like be comfortable manipulating strings, and that's pretty similar to knowing KMP. Like KMP is not too sophisticated if you understand strings, and this also kind of requires you understand strings. So it turns out that you can always get the answer down to 1 unless the string is all the same, right? Is that the case?
Yep, sorry. I got a bit AFK, but I'm here.
Oh yeah.
Sorry.
Yeah. So for problem E, I guess one surprising thing is you can always make sure the answer is just 1, right? That the maximum
Right.
match is 1. And so first of all, if there's a character that occurs only once, then you can use it. Then if you put it as the first character, then there will be no matches anywhere. So the answer will be 0, which is optimal, right? Otherwise, like you can make your goal is to make sure that the first 2 characters don't appear anywhere else in the string. And so I just
first 2. Right.
Yeah, so I ended up doing like a couple different cases, and there was I thought it was like a pretty I thought it was like a pretty reasonable problem with just a good amount of casework. I guess I can go through some of the cases I found. So one case I found was that so if it's all the same character, you just do it.
Pretty sure you found all the cases. Like you have to count. You kind of if trying to casework the problem, then probably you cannot really go too wild. Yeah, go
Yeah.
ahead.
Right. So the first case is the best case is, well, obviously you should start with the smallest character because that makes it lexicographically minimal. And then if you can start with AA, so the first question is like if your smallest character is A, like can you start with AA? And you can do that only if like there are enough things to like space in between the remaining A's, because you don't want any other two A's in a row, right? So you actually need like the count of the A's to be at most like 2 plus like the count of the rest of the things. In which case, if it is, then you do like AA and then B and then A and then like you do like AA and then BA, CA until you're out of A's, and then you can put the rest however. So that's how, like, that's the simple way to do this case. And if there aren't enough A's, if there are too many A's, then you can't start with AA because then you're guaranteed to have two A's next to each other later. So the second case is that otherwise you have to be able to start with AB. And if there's only two characters, you have to actually put all the B's next. Because if you do like A, B, and then AAA, then eventually you have to come back to B, and that'll be an AB, which is a bad repeat. So you actually have to do A, and then a bunch of B's, and then the rest of the A's. So that was this case. And then the final case is if there's some other character like a C, you can do A, B, and then all the A's, and then a C, and then the rest of the characters. So B's, and then C's, and then D's, and then E's. And so that I think those were all the cases.
Yeah, sure. I mean, those are all the cases, and
I guess there are a couple other cases. There are a couple cases with like if there's only one A or two A's. I guess I also made that a special case, but I think they actually don't. It doesn't actually affect the answer.
I mean, if you have at least two occurrences of each letter, then you should be fine, right?
Right.
Because you already have.
Oh, we already know that we have two occurrences of each character. Okay, so this case is actually redundant. Okay, I see.
Yeah. So I don't know. I don't have like a strong opinion about this problem. I don't think it's like too interesting or something, right? It's kind of. I mean, some people do enjoy it. I personally, I guess I do enjoy it as a process, right? So if you have the problem like this, it's kind of interesting to me to find out that the answer can be always one, right?
Right.
It's not a trivial thing. Like you have to figure it out. It's kind of an interesting fact. Yeah, and then like you figure out that you have different ways of actually putting the characters so that you have like the answer one, but you want to make the string as small as possible, and so on and so on, right?
Right.
So like you kind of work through it, right? One approach that could simplify your life maybe is if you know that the answer is one, or like, yeah, the answer is one exactly. You can try to like make a function that takes a prefix of our string and the counts of the remaining characters, and it says whether we can finish the string with the remaining characters, so that the answer is still one, right? And if you make such a function, you can try to form the answer string character by character, left to right, right? You just try to put every like a letter A here, and you check whether you can finish the string. Letter B here, like if you can't, and so on. If you can with letter B, then you put it there and proceed. And then the function itself, yeah, it still has to have two cases. Like the biggest cases are whether the first two characters are the same or different, right? If the characters are AA, you can have AA, so you have to like space the A's with different like characters between them. And if it's AB, then you almost always can finish the string without any more ABs, unless you only have like A's and B's, and the last character is A, something like that, right? So that could be an approach that kind of makes your like work as a case analyzer easier.
Right.
But maybe not by much. I'm not sure about that.
Right.
But yeah, it might be like still a useful trick.
Right. Yeah, that kind of trick is pretty useful a lot of the time because it lets you go from, instead of having to think about like, oh, what's the like globally smallest, you only have to think about like this one case, like is it possible or not. So instead of like the value, you just only have to think about this boolean. But in this case, it's it may or may not be a lot easier to code to actually find this kind of oracle that tells you whether it's possible or not.
I'm not sure. Like, is it actually that hard to code? I don't think that
Um,
code itself is like hard.
yeah, it has a lot of similar cases, I guess. So
Yeah, I
yeah,
don't know. Like I don't know. I wouldn't say that you have to try hard to implement the problem. I wouldn't call this problem an implementation problem. Like, it's a case analysis problem, that's for sure. But
right,
I don't know about implementation.
right. Yeah, yeah. It's just yeah. Um, if you go to videos and you click the most recent one, you should be able to like rewind in that video. Um, but yeah, cool. So yeah, yeah. I thought yeah. Let's move on to problem F. Problem F, I think. Problem F was pretty interesting to me. I'm mostly curious about what the complexity was supposed to be. Um, But problem
Let's
F
take a look
is
at.
you're given a n by n board, and there's some probability that each cell will happen, will be marked. So you're given some probabilities, and you win if you get a bingo. So you get any horizontal line, any vertical line, or one of the two main diagonals. Um, and so one thing to observe is that n is pretty small. It's at most 21. There are most 21 rows and columns. And so you can just do so I did a 2 to the 23 times n squared dp, um, but I don't know if you have any other ideas. So my dp was essentially like this cell by cell dp, where you go through each cell, and your dp state is whether each of the rows is a valid bingo so far, as well as whether the diagonals are a valid dp so far. And then also, and then you kind of you also keep track of whether the current column is a valid bingo so far, and then you like move these things along. Um, Vanilla asked why not use Skype. I don't really have a reason to use Skype or landline phone. Yeah, I don't know anything worse. Um, So yeah, my solution is I guess I usually call it like cell by cell DP or row by row DP, but a lot of people call it DP on broken profile. But yeah, that was my solution. Um,
Yeah, that
enable
was
D&D
your
in Discord.
solution.
Yeah, I can do that. Let me just mute this for a
Mm-hmm.
little. Cool. Uh, yeah. So what was the intended solution for F, or the intended complexity for F?
Yeah. So the intended complexity was 2 to n times n, not n square, right? You had n square.
Yeah, I had n squared.
Yeah. And this problem, like, I was probably most unsure about this problem in the contest, like whether it will go well in
Mhm.
terms of like how close solutions will be to intended and something, right? So yeah, one solution is definitely just cell by cell DP.
Mhm.
And then like when we discussed this solution, we kind of came to a conclusion that this solution is not interesting enough
Mhm.
as like on its own. Like some people just come up with it like instantly because like
Right.
I don't know. Like honestly, when I was coming up with the problem, it did not occur to me at all. Like that you can just do DP.
Mhm.
But maybe that's just because I was already thinking about a different way of solving the problem, and
Mhm.
that's inclusion exclusion.
Mhm.
So basically, you have first of all you have n horizontal lines and vertical lines and two diagonals.
Mhm.
So that's 2n plus 2 lines in total.
Right.
So you can try to do inclusion exclusion on all of these lines, right? That
Mhm.
would be too many of them, but you can still try to do that. You can solve the problem in that complexity. And
Right.
then the thing to notice is that you actually don't need to do, for example, you don't need to do inclusion exclusion on the rows. You only can do inclusion exclusion on columns and diagonals.
Mhm.
And after that, for each row, you just calculate the probability that no row becomes a winning, right? So you want to find the probability that your table is not winning.
Right.
You subtract the probability that some columns or diagonals become winning. And
Right.
then like if you choose some columns and diagonals,
Mhm.
you want to make sure that rows are still not winning. Like you for each row, you pick all the cells that were not touched by any columns or diagonals.
Right.
And like you find the probability that not all of these cells are like true, right?
Right. Right.
So you can do just inclusion exclusion on n+2 events,
Mhm.
and that's kind of it. That's kind of the idea of the problem.
Right.
And then like if you just implement it as is, you will still get 2 to like n+2 times n squared because you loop over all the cells
Right.
in the grid afterwards.
Mhm.
So, and there are at least two ways to optimize it.
Right.
Like this idea at least. So one idea to optimize it could be to use DFS.
Right.
Instead of trying to do all bit masks of columns, you can just do like go column by column.
Right.
You either include it or not into your inclusion exclusion, and you can recalculate the products for all rows in linear time. So it will become 2 to n times n, like overall complexity.
Mhm.
And another way to optimize it is for each row and for each mask of cells in this row, you can pre-calculate the probability.
Mhm.
And then like when you pick the diagonals and columns for each row, you can just, instead of running through all cells in this row, you can just take some pre-calculated value.
Right. Right. Yeah. Yeah, that makes sense. Um, yeah.
Yeah,
So,
so mhm.
yeah, I guess that's I guess it turns out that you can pass even with n squared in the end then um,
Yes,
without
sure.
the
I mean,
optimizations.
it was pretty tough. Like the
Right.
first thing I actually wanted to do was like set n up to 16 and just like let whatever pass, whatever
Yeah.
that works, not like that doesn't do inclusion on all the lines,
Hmm.
but only on some of them. But
Hmm.
then, yeah, like we decided that it's not worth to
Hmm.
just allow DP solutions because they're not interesting. So
Hmm.
we like I don't know. It led all this thing led me to doing like really weird things. Like first of all, the modular. Like
Hmm.
what do you think about the modular?
I don't really understand why the mod like I understand that the mod smaller means that you can like you can squeeze things into in 16s and stuff. But I don't really know why you did that. Um,
Yeah.
I did the n
So
squared times 2 to the end, and I one of my optimizations was using shorts instead of ints. So
oh yeah, maybe that's what I missed because I was trying to do the DP like the
right,
one you did, and
right,
my solution worked in like 9 seconds, I think.
yeah, yeah,
But
yeah.
you did it a little bit better,
I did
just
it a
enough
little bit
to get
better
probably.
because it I think the because the scan is essentially linear, so it decreasing the size decreases memory contention a lot because everything gets like it
Yeah,
has the number of cache misses. So
yeah, that makes sense.
yeah,
I mean, good job. I mean, I guess
yeah,
you beat me in squeezing DP solutions, so you
yeah,
deserve it.
yeah,
But
yeah.
otherwise, the reason for this modulo was just because if you use a usual modulo, which was like 1 billion or something,
Uh-huh.
suddenly, if you submit your solution under 64-bit compilers, it just gets 3 to 4 times faster.
Uh-huh.
And I mean, that's not unexpected because
Right,
like most of your computations are just taking 64-bit numbers modulo some modulo like a billion.
right.
But like you don't want people like to you don't want to distinguish people on whether they used 64-bit compilers or not.
I see.
So after that, it becomes really hard to like distinguish anything from anything. It's hard to make a reasonable time limit. And then with
Mhm.
a small modular, you only use like ints, right?
Right.
You don't need 64-bit numbers.
Mhm.
So it became kind of easier to find the balance.
Mhm.
And I think it still worked pretty well. So like the best solutions we had, which were like 2 to n times n, they worked in like 1.2, I think, like 1
Mhm.
second and a bit.
Right. Right.
And but some of the other solutions, like I even had solutions in Java which passed
Mhm.
in 2 to n times n, like they worked
Yeah.
in like 4 seconds, I think.
Yeah. Yeah.
So yeah, and also my DP worked in 9 seconds. So I saw at least one participant that implemented DP solution. It
Right.
got time limit exceeded, and it actually was like very close to mine. It was like 9 seconds,
Right.
and then they just had to re-implement to inclusion exclusion.
Oh, I
So
see.
it kind of worked.
I hit the 9 second case. I hit the 9 second value as well, but I was using custom tests, so I just kept optimizing. One thing that's
Yeah,
nice about
I
this
mean,
problem is you can pretty quickly tell, like the runtime is pretty much constant, so you know if you're going to pass or not.
uh,
Yeah.
yeah, that's sure. I mean, anyway, I think that one of the biggest things was to like try to not allow most of straightforward DP solutions. There are still some DP solutions which use like convolutions, right?
hmm Right. Those are
But
probably
other
even
than that,
slower.
but yeah, I mean, no, like some
No.
people did like convolutions. Yeah, that's
Right. Right.
somewhat faster. But anyway,
Yeah.
and then like I wanted people who actually implemented 2 to n times n to not feel bad, like to not have to push their solutions to squeeze
Right.
them.
Right. Yeah.
So yeah.
I think that's the way to do it. I think you should like make sure that intended solutions pass, and then like if optimized slower solutions pass, like if a few optimized slower solutions pass, that's okay. Um,
Yeah,
but
like
it's
if you actually go for optimizing,
yeah,
actually, like if you see the constraints, like 21, even though you have 7 seconds, but
yeah,
2 to n times n square is kind of a lot, right? So if you're
yeah,
going to squeeze that solution, then like it's
yeah,
your choice. You
yeah, yeah,
can do that.
yeah.
But and
I
also,
think
yeah,
it's like a
like
pretty
is
fair.
it Mhm.
It's like about as fair as it can get. Where if you
Yeah,
squeeze, if you
it's
spend, I spent a good like 15-20 minutes squeezing,
mhm.
and if you're willing to do that, then like maybe it's okay. But uh, like it's it definitely was a time sink instead of finding the intended solution compared to finding the intended solution.
I mean, so you spent 15 to 20 minutes and you managed to optimize it, but maybe some people actually like spend some time and just did not
Yeah,
progress.
yeah,
And then
yeah,
like it's their risk.
yeah,
And
yeah.
how many of the
It's just
solutions
risky that
were
way.
n times 2 to n? Actually, a lot. I think that most of the past solutions were n times 2 to n. Like I looked through a lot of solutions, and I think a lot
hmm
of them were actually
hmm
using either like one of the two ideas I mentioned.
hmm I see. I see. That's pretty nice. That is pretty good. Um, it's good that most people got it. The majority of official submissions took less than 5 seconds. Golovino says so. They're probably not squeezing. Cool. Some people are asking you to turn on a light. Um,
I'm not sure how easy that will be. Maybe you can
okay.
just
All right.
yeah
I guess it will just be dark mode tourist then.
yeah.
Okay. Cool.
um yeah. I mean we can just go. I'll try to do
Yeah,
something about it.
it's okay. We can just keep going. All right. Problem G. Problem G was pretty interesting. This is the last problem I solved. Um, I'll pretty quickly say the problem. The problem is you have two strings of length A and B. It's two strings A and B. They're the same length, and you want to transform A into B. What you can do is you can take any substring of A that has exactly k ones in it and reverse it. And you're trying to do at most 4 times the length reversals in order to make A into B. And yeah, N is at most like 2000 or something. So it's not a data structures problem. Imagine if it were the data structured version.
Could be.
That would be annoying. But yeah. So the solution, the first thing I thought of, the first thing I thought of was that it's actually kind of easier to, instead of thinking about flipping like strings of zeros and ones, I thought about it as you have like, you just keep track of how many zeros are between each pair of ones, or what's the distance between each pair of ones. And
I
this...
agree. That's useful. Sorry. Yeah, I think that's a good first step.
Right. And what the operation actually does then is, if you have
a little bit lighter then.
Yeah, that's a little better. If you have 2 gaps that are k apart, you can flip all the gaps between them, and then you can pass any amount of zeros between these 2 gaps. So if you have the gap between the 0 and the first one and the kth and the k plus 1, you can like kind of shift the zeros between these 2 outside gaps. Please no n log n constructive problem. Yeah, okay. That's pretty fair, Kevin. That would just be like, if it wouldn't change the like algorithm at all, it would just make it so that you have to code like a reverse, like a BBST, so that you can reverse and take prefix sums or something. It would just be bad.
That's what I would have to do for the checker, right?
Oh yeah, you have to do that for the. You would like actually have to do that for the checker, but I feel like you have to do that for the solution too, because you have to figure out the right offsets, right? Isn't that pretty tough?
Yeah. Like you can definitely do that, but you have to do like you probably have to do some BBST. Yeah, you probably can't do it without it.
Yeah. I don't know. Maybe you can find some closed form, but it sounds annoying. Yeah, the way so my approach, I solved this pretty close to the end. So I'll just explain my approach first. My approach was, the other thing you could that you can do about these problems is, instead of like trying to transform A into B, you can try and transform A into some canonical string. So maybe like the smallest string, or like the string with everything as far left as possible. And then you can transform B into that string in the reverse order. You can transform B, like you can like reverse transform B into that string. And in this case, because the operation is like it's the same as its inverse, you can actually just transform B into that string and then reverse the sequence of operations. Someone is saying that the leaderboard looks messed up. That's interesting. I assume maybe Codeforces is just confused. I bet one of these is an I. Yeah, one of these is an I and one of these is an L or something. So, yeah. Anyways, yeah. So you can you can just try and transform A into the smallest possible string and B into the smallest possible string, and then do A and then reverse of B. You'll be able to see other people's submissions after sys tests are done, so it should be like pretty soon.
Yeah, it's almost done. Yeah. Actually, maybe it's.
Oh, it actually maybe it just finished. So. Yep. Yeah. So one thing you can do is, because the operation lets you move the things that are k apart, what you can do is you can go through from the end of the string and from the end of the string and just move all the zeros between the last 2 ones into the between the first between like, you can move it k earlier. And you can like go through the string in reverse order and just move all the zeros to the front of the string. So then you can get all the zeros into the first like k plus 1 gaps. And then it turns out if you just alternate swapping the first range and then swapping the second range and then swapping the first range and then swapping the second range, like it actually just works. It's kind of funny. You have to set it up properly. So you want to make it so that everything goes to the very left as far left as possible. So you actually want to set it up so that if there's something in the whenever you do the swap, you like always swap all the zeros as far left as possible greedily. And you just like alternate these two. Like you do this swap and then this swap and then this swap and then this swap, and it it works. One way to prove it is by like considering these as like matchings, and like essentially like you have two matchings, one red matching, one blue matching, and every time like you can say red and then everyone walks along the red edge, and then you say blue and then everyone walks along their blue edge. And if you just say red blue red blue red blue, then like they always walk to one of the ends of the matchings. And so you actually set it up a little bit specially so that everyone walks like red blue, but that might be left or right, and you set it up so that like the right endpoint like reverses you around and like pushes you back left. And yeah, so you can just kind of alternate. Did you have a kind of similar idea?
Yeah. I think I actually don't have too much to add to this. So basically, you remove the zeros from all the blocks except for like the leftmost, I don't know, k+2, right?
Yeah.
And then yeah, you just alternate the reversals without the last block, without the first block, and so on. And then yeah, it turns out that if you just do that, do like reversals of this kind, every block will appear like. Actually, it's a bit different for even and odd, right? Okay.
Yeah.
Odd has to be different. So for
Yeah.
odd k, like there's like the second right position, which all blocks actually visit in 2k steps. I mean, it's actually like it's super hard to actually like try to explain it like
Right.
without any pictures, because like even when I was trying to solve it without actually like drawing something like what goes where and so on, it was very hard for me to visualize what was going on.
Yeah.
But
Yeah.
anyway, like yeah, the main idea is you like if you have at least k+1 once,
Yeah.
you can basically do almost everything, like almost
Yeah.
whatever you do.
Yeah.
And yeah, if k is even, then there is some invariant, because even blocks have the same sum, they don't change, because when you reverse, then the even distances only transform to even distances, even as in even position, right?
Yeah.
And then
Yeah.
same for odd. So you will be able to make two blocks of zeros, but you might not be able to make just one block.
Yeah. So what I was talking about earlier with the alternating colors is like if you think about the swaps as like there's a red swap, there's a red pair of swaps and a blue pair of swaps. They might look like some weird graph, but they always look like some kind of matching, and it's not too hard to show that they form like a single path. And what you can do is like if you have like if you like say like do the red swap and then do the blue swap and then do the red swap and then do the blue swap, like you'll have the person like kind of move along this path. But they might move in the opposite direction. So if they're starting here, then they do the red swap and then they do the blue swap and then they do the red swap or something. So they might move in either direction, and you can do a little bit of stuff to make sure that they go only one direction. They eventually all end up on the same endpoint. Just by like kind of adding self loops.
That's nice, I guess. Like
Yeah.
visualizing it as two matchings that form
Yeah.
one path is kind of
Yeah.
could help. Yeah.
But yeah, so it turns out you just do this, and I think you need to do like k, like 2k operations or something like that, 2k+1, 2k+2,
Yeah.
something like that.
Yeah. Well, probably not +1. I think it's kind of exactly 2k, but
Right.
well, maybe +1, whatever. Yeah, like you still fit under 2n. What's
Right.
the most important, right?
Right.
And so if you transform both strings into some canonical representation in 2n steps,
Right.
then you're fine.
Right. As long as each half is 2n, then the total is 4n. So it actually works out.
Yeah.
Um,
It could be possible to optimize the solution if you actually know you don't have to transform both strings into the same string. If you actually try to transform one string into the other, maybe you can do less steps, but I couldn't find anything like generic.
yeah, it sounds very at the very least it sounds very annoying to code.
Yeah.
Yeah.
And this problem.
You have to like be
It's
very
not
careful to
already.
make sure that things are getting to the place like sooner rather than later.
Hmm.
Yeah. Okay. Last problem. H, Turing's award. So the problem here is that we have a tape, an infinite length tape, and we're given a permutation, and we're going to write this permutation onto the tape in some way. What we'll do is we'll start off at cell 0, and like you write A1 on that cell, and then you have the choice of staying where you are, moving left or moving right, and then wherever you get to, you write A2 on that cell, and you might overwrite some old value, and then and then you either move left, stay the same, or move right, and then you write A3 in that new cell, and you keep going until you've written all n integers down, and we're trying to maximize the length of the longest increasing subsequence of this string. And so, I guess it's still not public. Cool. So, the way I approach this, the first observation I did was that if we're trying to maximize the length of the longest increasing subsequence, we can first like pick what the subsequence is, right? That's probably the easiest thing to pick first, and then we can say like, is it possible to write this sequence down on the tape without like in this way? So is it possible to make this an actual subsequence of B? And what you see is that the way the tape, one way of thinking about how the tape works is we can reverse time, and we can say like, okay, at the last point in time, like I had this, like I put down this value. If you keep going backwards in time, like you can kind of like write down values, and then they kind of have to be like outside of the range that like you've already written down in the future. In order to be visible at the end. So you can kind of like, if you want to prepend a number, you can like walk over here, like walk from here and prepend it, or you can like append it over here. And then once you have that kind of structure, then you just once you realize that, then you have these conditions on like, you're essentially trying to start from the end, and you're trying to like build this like sequence that like you can prepend smaller numbers or append bigger numbers. And we can do this with a DP that's very similar to the longest increasing subsequence DP, except we have to kind of like store both endpoints. And it turns out that if you're careful, you can make the number of states O of n times the answer. Like O of n times the maximum length of the longest increasing subsequence. And the answer, because the permutation is chosen uniformly at random, the answer is actually O of square root n. In expectation, because the length of the longest increasing subsequence, it's upper bounded by the length of the longest increasing plus the length of the longest decreasing in A, and those are each O of square root n in expectation. They're like 2 square root n in expectation or something. So that's my quick hand wavy node diagram explanation. So I ended up using like an ST map and stuff to store these. Was that kind of the intended approach?
Yeah, sure. Like, first of all, yeah, like the DP state. My first idea when I was creating this problem was like, you can do DP of left number, right number, and P state is the length, right?
Right.
Yeah, expected length is not log n. Yeah, it's square root of n, I guess.
Right.
And then, yeah, okay. So, and then, yeah, the main thing to improve is that you can actually move the value of DP into its state. And for example, you can do, if that's my number on the left and that's my length, what could be the smallest possible number on the right?
Right. Yeah.
And vice versa. If that's my number on the right and that's my length, what could be the largest possible value on the left, right? And it implies that like in the first case, I guess I stand in the leftmost number, and in the second case, I stand in the rightmost number, right?
Yeah.
So that's why we have n times answer states. which is n square root of n, as you said. And then there are like many different ways, maybe not many, but at least a number of ways to go from there. So if you just try to loop over the next number, you will have n transitions from each state. So it will be like n square times square root of n, which is n to 2.5, right? That's too much. So what you did, I'm not sure. Like I guess you went like how did you optimize the? I mean, I guess I can figure out how you optimize the transitions, but there are two a bit different ways, I think.
Yeah, so I optimized the
So,
transitions by using like an STD map. I actually just stored the things you said. I kind of stored like a map of like for each left endpoint, for each value. I stored a map for each value for each length, and I stored like a map from the left endpoint to the best right endpoint, and then I like as you insert things into the map that are better, you can like actually delete the things that are like delete any ranges that include it.
vector of Pareto sets, I see.
Yeah.
Yeah, that's yeah. So the thing is, I will try to kind of explain my solution to me. So you're going through positions in permutation from right to left, right? You're
Right.
trying to take every number and then do transitions based on that number.
Right.
But actually, you can do it differently. You can do like you have like again, your state is number and length, right? You can do kind of layer DP. You can go
Right.
from length to length plus one.
Yeah.
Instead of going through numbers, you do
Uh-huh.
transitions from layer
Does
to
that
layer.
does that kill the log factor?
No, that does not. It
Uh-huh.
is still n square root of n log n. Like you can do transitions. So the transitions will be, for example, like if you have some number on the right, you can, and you want to put another number on the right, it has to be to the right of that number in the permutation, like
Yeah.
to the left actually, right?
Yeah.
And it has to be bigger. So you have some kind of two-dimensional queries,
All right. And
and
so
you
we
can
still
do
plane
kind of
sweep.
like sweep line, yeah,
Yeah.
with like I don't know, Fennec trees enough.
Yeah.
So
Yeah. I
the
mean, in some
logarithm is
sense,
quite small.
I'm just doing the sweep line for all of them at once, right? Something like that.
Yeah, kind of like you're not going from like you kind of do the same transitions, but in different directions, so you cannot
Yeah.
use the same data structures, right? So you're
Right.
using different ones.
Yeah.
But like the thing is, actually, my solution works in like 0.5 seconds, and yours
Yeah.
like 4. And
Yeah.
I saw
Rainbows is
some
also
other
like
submissions passed in
600s.
like 9.
Right.
Yeah. So it was also a bit of a challenge to actually set constraints and time limits correct in this problem, because like you don't even know what correctly is, right? You have
Right.
some solutions, and you like this data is random, so
Right.
it's not like you can
Right.
like yeah. So the thing is actually like Kevin implemented a solution which was similar to yours in the idea, and it was even slower than yours. It worked like in 6 seconds or so.
Right.
And initially, I wanted to set time limit to 4 seconds or something like that. And based on the fact that actually there is a different solution, which is also like which has the same complexity but works like 15 times slower.
Right.
I decided that okay, I guess we can like just increase time limit and
Right.
maybe it will work.
Yeah. Were you
I
were
guess
you
it worked.
were you worried about any n squared solutions passing? Do you know if any of those managed to squeeze in?
I did not. Yeah, like one way of doing n square, like there's different way of doing transitions in our DP.
Right.
For example, if you consider like I said, from number, you want to move to all numbers to the right of it, which are
Right.
bigger, right? In fact, you only need to move to numbers which are not dominated by other numbers.
Right.
Like if you see what dominated means, like right?
Yeah.
Like if you
Our prefix maxes
visualize them
or
as
whatever.
points, yeah.
Yeah.
Well, kind of like you only consider numbers bigger than and to the
Yeah.
right. Like you
Yeah.
only consider some part of the plane, and in
Yeah.
this part of the
And it's
plane,
kind
you
of
only
like
consider like numbers.
the line. Yeah.
Yeah. But like the thing is, there are only log of transitions, right? You actually need, which is kind of interesting. So you can actually do n square root of n log n transitions. but it's a bit tough to find the exact points where to move.
I see.
And so one of the solutions we had from Nikolai Kalinin was like it was doing the same n square root of n dp, but he was finding the points to make transitions to in n square. He had some n square precount. And but that's basically it. I didn't know, I still don't know any solutions which like work in like pure n square time. I know n square log n, which most definitely should not be enough, and I don't know really any n squares. So I was a little bit like afraid. I like actually the reason I didn't want to set n to like 10,000 because like I think with 10,000 you don't really expect that the expected like solution is n square root of n log n and not n square. Like 10,000 is like just screams n square, right? So I kind of didn't want to bait participants into trying to come up with n squares. So I wanted to set constraints a little bit higher, like 15,000, which also led to a little bit too high time limit maybe, but I guess it's fine.
Yeah, I think the time limit was fine. I think this was, as long as you fail the n squareds, like that's pretty good, pretty consistently. The n squared log
I don't know any, and n squared log n probably fails.
Yeah. Golovino says that Rainbow is H passed in 600 ms. I think Kennedy said that his solution in C++ also passes in like half a second or something. So I think they just have better solutions than me.
Yeah, actually, Rainbow's code was pretty similar to mine. I think it was
makes sense.
Basically the same solution.
Could I have hacked someone and gotten number one? Yeah, that's a good question. I meant to like hack a random person.
Do you have any failed solutions in the room?
But I don't. I kind of doubt that I have any FSTs in this room. There actually was one. I didn't check it, but there actually was one. TLE on test 4 on problem C.
Okay, TLE.
All right. Wait. Well.
Okay. What? Wait. How can it? So it passed pretest and then it got TLE on pretest, right?
And then TLE on the same.
I mean, I guess something must be wrong, but you know.
That's
okay.
Strange.
At least I had a chance.
Yeah, I guess I had a chance. There were a lot of things I could have done to like get 20 extra points, and there were also a lot of things that Xiaolong could have done to get like 29 extra points or whatever. So like an extra couple points on top of that. So the what ifs are only so useful. UB, yeah, maybe it's UB. Yeah, people are saying that they still can't view other submissions. I don't know if you know why that is.
Okay, I'll guess I'll ping someone.
Yeah. Yeah, it's still not in practice mode. So I wonder if Mike might just be running some plagiarism check or something like that.
I guess that should not like.
I don't know. But yeah, GG's. So I saw one other thing that people mentioned was that Scott got FST on H. Wrong answer on test 83. Oh no. Yeah, I think before this he was talking a little bit and he was saying that his code for H was very nasty and like he had a bunch of cases. I don't know if he's I don't know, Scott, are you here? Do you
that's kind of unfortunate. There was a lot, like I think there was like 94 cases or something like that. So he was actually pretty close.
He was quite close.
And also like what he can actually like he can check it later anyway. So actually the submission before the last of his submissions actually passed system test.
Oh wow.
The one
okay, so he actually
but it took more time. Like I'm not sure what he was actually doing. Because like that submission passed in like 9.999 seconds,
Oh wow.
And then I guess he just lowered the constant to make it more probable to not pass, and then the last submission was a bit faster, but that exact bit was the reason to fail, I guess.
I see. Interesting.
Really unfortunate, yeah.
Yeah. Man, that's unfortunate. Yeah, he was telling me that he did a lot of like square roots. Like he has like 3 or 4 different constants in his code. They're like different square root bucketing constants or something.
Yeah.
So
I mean, in some sense, this problem is kind of like there are no like the test cases, right? Like in problem
Right.
F again,
Right.
you can just generate the biggest case and
Right. Though I guess it might be difficult to. I guess you can like pick worse constants in diff or something. Pick different constants in
yeah, I
diff.
mean, yeah, the answer changes a bit, right?
Yeah.
And I guess the number of states in whatever you have that could also change from test to
Right.
test. So yeah, you have to
Right.
run a bunch of cases.
Yeah. Yeah. But yeah, yeah. Overall, I like this contest. I thought the problems were pretty interesting. I thought, yeah, G and H were both pretty interesting. I think, and I uh, I had fun solving them.
Thanks. Yeah, I guess this contest is actually it's probably stronger in the harder problems. So it could be
Right.
a
Right.
little bit
Well,
boring in the first problems,
I'm
but
dude.
overall.
I'm so bad at remembering problems. I don't remember problems I solved like problems I worked on like a day ago. So I just legitimately don't remember any of the problems from more than 2 hours ago.
All right.
Yeah, yeah. That's pretty much
Um,
how it works.
so
Um,
so I guess the biggest achievement should be to write a problem which you will remember after a day, and
it
then
takes
after a week, right?
yeah, yeah. But those are usually problems that I don't solve because I have to keep thinking about them.
Okay.
Yeah, so
I'll try
those
harder
aren't
then.
necessarily the great problems.
I'll try to make problems you won't solve. That's fine.
Yeah, yeah. When do you think GitHub Copilot will wipe all these problems? I don't know. Probably never, or like probably not. Maybe in our lifetimes, but not for a long, long time. It'll be a while before before like Copilot can do algorithms. Was there any time ago there was problem like F but without diagonals? Do you know that?
Yeah, I don't. I mean, that's another concern I had about problem F, that it could be, I don't know, well known in whatever country,
Mhm.
or like even well known, I don't know. Its statement is a bit too simple, right?
Right.
So that could always be the case. But I don't know. I didn't see any links yet. So if
Yeah.
you have like if you know any similar problem, then like do share.
Yeah.
I would just be curious in any case.
Mhm. Yeah. 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 I haven't seen something like this, but it does look. It looks like it looks simple enough that it might have occurred before. So
Yeah, that's kind of the thing.
yeah. 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 No, there's no way that Copilot can solve Div 1 hard algorithms. Like I doubt Copilot might be able to write like a valid seg tree, but it sure as hell can't solve the whole problem. um, cool. Yeah. So that's pretty much all the problems. Do you have any other like things you wanted to add about the standings or any of the after assist tests are done?
Well, not much changed, right? So
Yeah. Yeah.
I like it. Like Noshi 91 solved H and didn't solve E. It's kind of fun.
Yeah.
Um, yeah, I mean, not much to add.
Hmm.
I enjoyed preparing the contest, so I hope some of you guys enjoyed solving it. And yeah, come. I mean, I will probably take part in preparing, or maybe even prepare the whole BK Cup finals, which is
Hmm.
happening in a month.
Okay.
We'll see if I will have enough hard enough problems, but in any case, so yeah, join for that one too, and
Yeah.
see you all.
Yeah. Good talking to you. Thank you for the contest.
Yeah, thanks a lot for inviting me as well, and
Yeah.
yeah, see you soon.
Yeah. All right. I
Bye,
think.
everyone.
Yeah. See you.
Yeah, go ahead.
Yeah, I
Anything
was just
else?
gonna say I think I'm gonna end the stream now as well.
Oh, okay.
I have something else to do, and it's also lunchtime. So let's see if there's anyone that's coding to raid. Um, uh, let's see. Live channels. Do any of you guys have questions? My round when? Maybe sometime. Maybe sometimes. Not in the immediate future.
Do you have any problems which you, like? Do you have any problem ideas which you?
I have a few problem ideas, but I'm obviously not going to say them on stream. Maybe it'll be an open cup or something. That I'm thinking that maybe that's the best time. Some of these ideas are a little bit not quite suitable for Codeforces. So
Yeah, for
maybe
sure,
it'll
like,
be that kind of thing. But
not every problem is suitable for every contest. That's for sure.
yeah. So we'll see. Anthony writes code. Are they coding? Are they streaming right now? Sure, we can do that. Yeah, I'll try and upload this stream on YouTube. So yeah. All right, see you guys next time. And say hi to Anthony. Bye-bye.
Bye.